Hello, Integrated Math 3 and Integrated Math 3 Plus. Welcome to Lesson 11-2. Now, we've been playing around a little bit with quadratic inequalities, and we were playing around with some graphs and some tables, and we realized that the graph was kind of a little more handy than the table. The table was fine, but the graph was better. We're going to look at a slightly different situation here. We're going to start off with question 6. We're going to work our way through questions 6, 7, and 8, but of course we're going to start off with 6. So last time we were talking about dog kennels, and they had to have a perimeter of 50, and we wanted them to be rectangles with an area of at least 50. Here we have a different situation. You chuck a ball up in the air, you chuck the ball up in the air, and eventually it comes back down. The height of that ball is actually a function of time. You guys have done this. You probably did this so much in Math 2 last year. You did this so much in Math 2 last year. And it always ends up being a quadratic because gravity does that. It's a thing. Someday when you take calculus, you'll understand it better. It's freaking awesome. But here's the deal. When a ball is thrown upwards from a tower that is 31 meters tall, and of course, when you chuck it, right, when you throw it up, you give it some kind of initial velocity. And in this case, it looks like that initial velocity when I throw it is 24 meters per second. So the height of the ball above the ground is meters is given by this function. You're going to need that to help you do question number 6. So there's my 31. This is how we were standing on a tower. It's 31 meters tall. That 24 is that initial velocity when I threw it. And that negative 4.9, that's 4.9 meters per second, is gravity. Yeah, that's gravity. Negative 4.9 meters per second, because of course it's pulling down toward the ground. That's what gravity does. So here's the deal. You would like to know when the ball is less than 40 meters high. I would like you to write an equality that would describe that for question 6. And then for question number 7, I'd like you to graph it to solve the inequality. Go ahead and hit pause to work these out. Hit play when you're ready to check your work. All right, first of all, I want to know when the ball is less than 40 meters high, which means I want to know when this lovely quadratic will be less than 40. Yay! So I wrote that for question number 6. Now for question number 7, if you recall from last time, I'm going to graph it. So I'm going to do y equals my quadratic over here, and I'm going to do y equals 40. I'm going to graph them both on top of the same graph there on question number 7. So I did that. I noticed it was equal. It looks like it was equal. And again, I had to use Desmos to get exact numbers there. But I did use Desmos, and it looks like it was equal at about 0.4 and at about 4.5. Now, this one's a little different than last time. If you recall, last time we were looking for where it was above. But now I'm looking for less than 40. That's right, less than 40, guys, which means I'm looking for where it is below 40. And again, we're using our x values to kind of do that, but I can see 0.4. If it's less than 0.4, then that's where my quadratic drops below 40. And we said it also hits at 4.5. And when it's more than 4.5, then that's also where it's going to be. Hang on, I want my little guy back. I want my pen. Then that's where it's going to be less than 40. So I'm going to say, and it's not an x this time, it's t, right? So I'm going to say, all right, it's cool. When t, and I do have a pen somewhere. Maybe I have a pen. I don't know. Oh, there it is. Now I've got to erase it because it looks bad. It does look bad. I'm erasing that. I want my pen back. This is better. There, that's better. So we're saying when t is less than 0.4, we go And, or we said the other option, so I'm going to put or. So when t was less than 0.4, it was fine. We said the other option is, oh, that 4.5. When it's greater than that, we were cool. So when t is greater than 4.5. Now I'm going to point out a few little things. One of the things I want to point out is there is no squashed equal sign here. So there is no squashed equal sign there. That also means that if you wanted to use interval notation, this means I'd go from negative infinity to 0.4. And it would be open at 0.4 because there's no squashed equal sign. Or, do you remember our or symbol? Remember we had and or? Do you remember those? I always forget which is which. Or we go from 4.5, also open, to infinity. Now, I want to point something out. This is all fine and good for our graph, but question number 8 is pointing out something important. Guys, question number 8, can we look back at the problem situation at what we were, doing? I want my arrow back. Can we look back at the problem situation and what we were actually doing here? And I'm going to erase these now. Go away. Go away. Go away. Get rid of them. They're in the way. Remember our problem situation was a ball being thrown up in the air and all of that good stuff? Guys, question number 8. I hope you considered the problem scenario a little bit there. Guys, question number 8, it doesn't go to negative infinity and positive infinity. For crying out loud, this is a ball. When it hits the ground, it's done. When it hits the ground, it hits the ground. It's not going to burrow itself deep into the earth. It's just a ball. We're not throwing drills. Jeez. The other thing is, of course, time is not going to be negative. So there are a few things we need to keep in mind. So this is going to change. I want to do t is less than 0.4 and t is greater than 4.5. But because my time can't be negative, then what my interval actually ends up being is from 0 to 0.4, right? Open, and that one can actually be closed. That's okay. And the other interval then is going to be from 4.5, so 4.5. And while my time is going to be positive, my height's not going to be negative. It looks like it hits the ground right around 6. So I'm going to say I'm going to go 4.5 to 6. And again, it can equal 6, but it's not going to, I don't want it to be equal to 4.5. We want less than 40. So guys, yeah, you got to keep in mind the problem situation. You always should be keeping in mind the problem situation when you do these problems. Like, you did great work. This was super good. But remember, time is not going to be negative. My height is not going to be negative. So that might change your intervals just a little bit, okay? Make sure you're paying attention to the question and you answer it in a way that makes sense. So less than 4, so from 0 to 0.4 seconds and from 4.5 seconds to 6 seconds is when the ball will be less than 40 feet in the air. So there you go. Let's go to another question, see if we can kind of help. Come back to our pendulum. Remember our pendulum? Hello, pendulum. You're back for more. Why, of course. Remember how on the earlier problem we were like, what if we wanted to speed up the clock and annoy our parents, make it go faster? So remember how we set this up way back in the overview on student activity sheet number 1? And we set this up to be less than 0.8. So again, grab Desmos, play with this a little bit, and see if you can figure out what's going on here. Pick at least a point to the left and a point to the right. Tell me what they mean. And then I'd like you to answer question 10. What pendulum lengths would ensure that the pendulum takes less than 0.8 seconds to complete one cycle? So go ahead and hit pause to answer questions 9 and 10, and then hit play when you're ready to check your work. The first thing I did was the intersection because it was kind of easy, but I worked my way up toward it. So I'm going to work my way toward it. I need to get rid of that because it's in the way. I'm going to work my way toward it. So start at 0, and then I work my way toward it. And it looks like, remember, it intersected at about 15.9, right? So values of x that are less than 15.9. So when my pendulum reaches a length of 15.9, when we have values of x that are less than 15.9, it's going to take one cycle less than 0.8 seconds. Now, of course, if we keep going, boom. If we keep going, of course, you can see that once my pendulum length gets longer than 15.9, then that means it's going to take more than 0.8 seconds to complete one cycle. So with this in mind, I hope you were able to answer question number 10. Looking at your graph, it looks like from 0 to 15.9 is going to give you your chunk of answers. Maybe that's not the right word. But all of your answers should be between 0 and 15.9. You could pick any pendulum length between 0 and 15.9 centimeters, and you're gonna speed up that clock, and your parents are gonna wonder what the heck is going on with this. So graphing is a really useful tool, and it's really great that we can use these graphs to help us solve quadratic, and actually we also just solved a square root inequality. And while graphing is really awesome and it has a lot of advantages and it gives a really quick picture of the solution, there are some problems. For example, we've been using Desmos and I've been using my computer graphics and my animations here to show you how this works. However, if you're graphing it by hand, suddenly it's a whole new ballgame, right? Without all that technology, you may not be able to draw the graph very well or accurately enough to find a good solution. Or it might be difficult to find an exact solution, right? Like I wouldn't have been able to graph this by hand and figure out that it hits at exactly, it hits right at 15.9. Like that's insane. So while graphing is awesome and it's great if you have Desmos open and you can graph it and find your stuff, there are some problems. If you don't have the computer in front of you, suddenly it's hard to do. So next lesson, we're going to start talking about how we can use some algebraic techniques to help us solve our inequalities when graphs just aren't going to cut it for us, or they just maybe aren't an option. As always, guys, I hope you found this helpful and I hope you found this useful. If you've got questions or concerns, please feel free to email me or come see me after school Tuesdays and Thursdays. You know I'll be around, and I'll see you soon.